In this video, we'll continue our discussion of Green's theorem by applying it to circulation. So we're going to find the circulation of this path C. So consider the vectored field y squared x squared on the half annulus, which is a half donut, described right there as that set, whose boundary is C. Find the circulation on C, assuming it has orientation shown in the figure. So notice it does go counterclockwise. To use Green's theorem, we are going to have to verify C and C and R. So we'll do that first, and then we'll talk about the problem. C is simple, doesn't overlap itself. It also is closed. So we have both of those. So C is good. R is connected. If I take 2 points and I put them in R, I can keep it in R by connecting them. Right? I can draw a path from there and keep it in R. And then simply connected means I put any open set in here, and I can contract it down to a point that is still in R. Okay, that applies too. So we can use Green's theorem. Now, remember what circulation means. This is how much of the vector field is applying to the tangent unit vector, and what that means is how much headwind or tailwind do we have. It's a measure on that. If it's positive, we have a lot of tailwind. If it's negative, we have a lot of headwind. If it's zero, we don't have any kind of force pushing us forward or back based off the vector field, meaning it would be orthogonal, and that would apply to flux. All right, so if we take a look at our boundary here, C, and we're going along this boundary, you can tell here the force is pushing us along, and then here the flux is applying. Oops, that will straighten if I go too slow. This is going forward, and then notice the vector field goes left or right, and then now it's against us. That's against us, against us, against us, against us, all the way down here until we get down here, right? It's going to do that, so let me just do this real quick. And then we're going to cross the fluxes left or right, and then we go with it, and then it's against us, and then flux. We have flux going right to left, right? So it wouldn't be contributing to our circulation. It was kind of hard to tell, but you can see it starts here, and we have all of this going against us, and then we have all of this going against us. There is more, and then these are negative here, or zero, I mean, there's nothing, and then the going with this were the spots I didn't super highlight. So we have more super highlighted, more blue there. Sorry for the bad sketch, but that's the negative. We have more headwind, so that means the circulation on the boundary of R is negative. We have a lot more headwind than we have tailwind. All right, so let's show this now, because we can't just look at the picture and I guess that's science, but let's do some math to confirm it. So circulation. Okay, remember that circulation is of a closed boundary on a path C. M dx plus n dy. We have an m and n here, so I'm just going to fill those in. M is y squared dx plus n is x squared dy. We can use Green's theorem. We have that, so I'm going ahead. This is m, this is n. Let's go ahead and calculate m. Be careful, this is circulation, so we have to do the opposite. So we are going to m with y, and that's going to be 2y. And then n with x, which is going to be 2x. And remember, we do 2x minus 2y. So I'm going to rewrite this, the double over r of 2x minus 2y. It's using Green's theorem of dA. Now, think about that annulus, the half annulus, and trying to do rectangular coordinates over that would be pretty difficult, especially we have multiple, this is the bottom and top, this is the bottom and top, and bottom and top. We have 3 sections. If I wanted to use y, x is not any better. So this calls for polar. So if we take a look, and we were going to look at that annulus to try to describe r and theta, it's not hard to do. If we look at r, it goes from 1 to 3, and then theta, it goes from 0 to pi. Just calls for polar. So this is theta from 0 to pi, and then r is 1 to 3, and then we get 2r cosine theta minus 2r sine theta, and then we introduce this as polar, so it's going to be times r dr d theta. It's a very easy integral to solve. going to polar here just makes perfect sense to do that. So I'm not going to work this out because that is a very easy integral. In retrospect, there are no hangups there. It's a straight integration the whole time. No U subs even. So if you work this out, I'm not going to use video time for that. But this works out to a -104/3.